So, how you guys doing today? Good. Good. Alright. So I don't know if you guys watched the Wednesday one. We started the review from Wednesday. So let's do another review today. So maybe we can try to do this one. Okay. So I'll give you about 1 or 2 minutes. Try to do this together. And then the point here is make sure you also have some implied hydrogen subject too, right? Okay, 30 seconds. So what happened to this one here is the bromine comes on first because this will pick up one of the bromine here. Then they form the bromonium ion, which is this side. Initially the double bond is gone, right? This side is taken by one bromine here, forming bromonium ion here. So when they break apart, the water only came onto the other side. Okay, and also this was initially transformed, so the other methyl group and hydrogen and all are now put aside. Okay, it's because of how they approach to the double bond. Double bond goes to one of the bromine here. They form the bromonium ion. So this part already occupied. So water only comes to the other side. So, okay. All right. So, do the next one. Okay. Well, we try. Okay, let's try this one. Okay, about 1 or 2 minutes. Okay. Okay, about 30 seconds. Okay, so here's two things you can do, right? Okay, so if this is number 1, number 2 on your exam, which one is the right answer? So you have a hydrogen and bromine addition here on alkene. I put either hydrogen here, here, and bromine here and here. So it's 1 and 2. Which one looks better? Number 1 or 2? Perfect. Great. Okay, right? Because here's the thing. When they try to grab proton, the hydrogen first. They put the hydrogen on here, that makes the carbon-cation position at the terminal carbon, which is not so stable because the carbon stability rule. So they're actually gonna put this hydrogen on the end. Then you have a carbon-cation position in this carbon, which is what? 3 carbons around it. So it has a higher carbon cation stability. So then they're gonna do with the bromine anion comes in attack. So this is the better option here. Okay? And normally we don't show the hydrogen, right? It's implied. So makes sense, right? Right?
So it doesn't need to be a wedge or a dash or whatever.
This one you could do it.
Okay.
Yeah. Yeah. But the thing is, you need to know where they're attached to. Yeah. That's. Okay. The next one. Oops. Okay. Okay. That one.
Is that AC
Which one?
after the
The
silicon?
OAC. Yeah.
OAC, yeah.
It's acetate. Mercury to acetate. Okay, about 1 minute. We'll do this today. Okay. Yeah. So what happens? This one is this one. So this one will become this first, and they form the mercurium ion here. Okay, and then they're gonna open to the here, so you can have a better position to carbon cation, and water goes into this position. Okay, so and then this mercury group will be replaced by hydride from the sodium borohydride. So this will be gone, replaced by hydrogen, and this is water. But another hydrogen proton will pick up by another water, so it'll be hydroxy group here. So this is okay. So the trick is here. Okay, so the trick is if you have this one over here, remove the double bond. Okay, remove the double bond here, and look at which one has more stable carbon cation position from this one, where you had a double bond, 2 carbons, right? And this is where you had a more substitute, 3 carbons around this one, 2 carbons around this position. And then this is where you're gonna put OH. That's it. That's the trick. Okay. So if we have maybe something like this one, right? Okay. Then same thing. So you look at the alkene compound, try to remove the double bond, and you had a 2 position. You can add hydroxy group. Okay. Well, actually it's water, but it becomes hydroxy later. So this is a 2. Maybe this is a 1. Where you gonna put the OH? Perfect. That's it. Because hydrogen you don't have to show, right? It's hydrogen here, but you don't have to show. Okay. Make sense, right? Okay, that's the trick you can have. That's very good. Let's move on. Alright, let's do, okay, this is also kind of easy trick you can do. This is a reduction with the palladium on charcoal. Okay. So remember, it's a reduction. Okay. It's a reduction, meaning it will be saturated with the hydrogen. This is unsaturated now because it's double bond. Okay, about 1 minute with this together. Okay, about 30 seconds. Okay, so here you go. You can compare the. There you go. Okay, so the trick is what? It's pretty simple, right? You just need to reduce the double bond here. So we here and here and here. Okay, and then I'll give you one exceptions, several exceptions here. So if you have benzene ring, this conjugate because it's double bond, single, double bond, single, double bond, single. But for this orgo 1, I'm just gonna give you benzene as an example. We'll do more on orgo 2. This one cannot be reduced in just a regular reduction here. You need to have a very special conditions to do it. Either you can use very high pressure, high temperature. Either you can add a room temperature, a special element, rhodium. Then you can reduce the benzene, but this regular common, this palladium charcoal way is impossible. So if your benzene goes in here, it just stays the same. Okay? Nothing happens. Okay? And then one more thing is if you have this one will not be reduced unless this carbonic group in benzenic position like this. Also, it cannot be reduced in the regular way. Okay, stay the same. Okay. So if I give you,
So nothing happens?
nothing happens
Okay.
for this the regular reduction. You need to have a very special condition for benzene ring and carbonyl groups. So if you have this one, okay, maybe this one, okay, and then you can only reduce the one in the ring because it's not conjugate, so it will be gone, and this can be gone, but carbonyl group would not. Okay. So this is the separate exceptions. So you can look at the double bond with this reduction. You can remove the double bond by adding hydrogen there. Okay, adding hydrogen there, but the carbonyl groups and the benzene ring, conjugate ring, still cannot be reduced in this way unless you have a very special conditions. Okay, so if I give you this, just the one that is in the double bond, not in the benzene ring or the carbonyl ring, can be reduced. Okay, does it make sense? Let me give you one more example. Okay. Let's do this one. There's only one portion you can reduce. Where is it? That's the question. Okay, so we could only do this one because those are the exceptions. Makes sense, right? Let's move on. All right, okay, how about this one? Okay, so a germanium tetroxide with the sodium sulfide and some water. Okay, about 30 seconds. We'll do this together. Okay, so this is what happened. So the point here is your hydroxy group should be on the same side because if you look at the germanium, now it goes to and here, and then when so this will be on the same side, right? And then when you had a sodium bisulfide, and then would detach as that one, okay? And then they're gonna further reduce on this oxygen by water. Okay? So this is why these two methyl groups are pushed on the back. When they're coming onto the front side, they push on the same side on the back, and they stay on the front side. Okay, so there's another way you can do the similar thing. I'll just show you. I don't know if I'm gonna put this in the exam, but this is the okay. So if you have a certain type of epoxy acid compound here, what happens to here is they can actually form epoxide. Okay. So if that happens, okay, let me actually get to here. So if that happens, they can form the epoxide. This, okay. So it says a hydrogen on the back. I'm not going to show you because it's implied, but you can treat it with acidic conditions and with water. And this will be reduced by hydrogen, right, plus charge. And because they're forming epoxide, once they break to get the neutral charge, another water comes onto the back. Because the epoxide is on the front. So water should go to the back, right? So in that way, this is now, the oxygen is reached by a hydrogen. Okay, over here, okay. This is the hydroxy group now. But in the front, on the back, will be water. So initially it was water, picked up by another water, the proton. This is gone, and this is gone. So in this way, your diol, the two hardest group also on the opposite side. But the aluminum tetroxide will put the two hardest group on the same side. So that's the difference. This is the two contrast example we can try. Not sure about this one though on the exam, but please make sure to remember that the diol form on the same side one with the aluminum tetroxide. It's quite important. All right, let's try this one. Okay, about 1 minute. Okay, 30 seconds. Okay, so here's the trick. Okay, so as I mentioned before, they go through molybdenite, ozonide, and breakage by the next city condition. But what you actually need to do is just cut this in half where you have a double bond. Okay, and put oxygen. That's it. So they break apart as two. So this one will be one. Okay, for this one, the other one will be one. Pretty simple, right? Just a double bond, break it, and put the two oxygen. It's what we call ozonolysis, right? We break the alkene with the ozone. All right, let's do one more. This might be a little bit tricky, but just the same mechanism there. So you can try this one, okay? But we'll do the same. Okay? Yeah. Okay, just break the double bond and put the two oxygen. That's it. Okay, it's a pretty simple trick we can do. Okay. So yeah, let's do this. Okay. So break this one, right? And then oxygen here, right? And there's implied hydrogen there, right? So it'll be 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So they just open. Makes sense, right? Yeah.
That like breaks the ring structure.
Yeah, because it breaks the double bond. Right? Yes. So in this case, it won't be break apart as two because it's a ring structure, right? So they still there, but it's still you break the double bond with the carbonyl group formation. Makes sense, right? Okay. Maybe can you guys try this one? Same mechanism. Same. Okay, so 1, 2, 3, 4, 5, 6, right? One, 2, 3, 4, 5, 6. Okay, so break this one. O, O. There's an obviously hydrogen, right? 1, 2, 3, 4, 5, 6. Okay. Makes sense, right? Okay.
Why
Can I
did
move?
you, why did you put the oxygen one on top, one on bottom?
Top and bottom. Oh, because you don't have to. Because you know, the single bond can rotate, right? So if you wanted to do it the off, I mean,
Okay,
as
so
long
it
as
really
you
doesn't matter.
no, because it's a single bond, right? Single bond can't rotate. So only thing you have to worry about is what? The double bond and the triple bond. Makes sense, right? But that way it's just easy to look at this one.
Okay.
All right. Let's do. Okay, let's try to do some triple bond. Okay, this one. So you should be able to look at this one, okay? By looking at that. Yeah, about 1 or 2 minutes. Okay, about 1 minute. So it's a triple bond now, right? So we're gonna do the similar thing what we did for alkene, but just a little more because it's triple bond and it has access. It's a lot of them. Okay, so yeah. This one. So there's a implied hydrogen here, but you know, going to show. So the bromine coming into this position because the higher stability of a vinylic carbocation. Okay? And then one more. Okay? It's the same. It's pretty much the same as your alkene, but it's just one more step because it's a triple bond. So once you get there, okay. And one more hydrogen. Okay. So yeah, just okay. Let's do one more with the halogenation. Okay. How about okay, so if you look at this one, you should be able to look at this one, okay? Because you know how many bonds can be made on carbons, right? Everything. about 1 minute. Okay. All right, so let's do this together. Okay. The point here is because of the formation of the bromonium ion, they're all coming into the opposite side, but eventually the other one also goes to the opposite side. So we fully brominated on this alkynes. Okay, so can I move on, right? Can you guys name this one maybe? It won't be on the exam, but can you guys name this one maybe? It won't be on the exam, I promise you, but I'm just curious if you can. Based on what we learned before. So the base is where? Here, right? So it'll be butane, right? For sure. So it'll be 4 bromo groups there, right? So it'll be perfect. Wait, 2, 2, 3, 3, tetrabromobutane, right? Okay. Oh, that's great. All right. So just same, yeah, all same principle for nomenclature.
Extra credit.
I think it will too. But... Okay, so you can just try this one. Okay, yeah, this one. So almost the same mechanism what we did with the alkene, but it's alkyne. So yeah, that's the only difference. Okay. About 30 seconds. We'll do this together. Okay. All right. So here's the thing. Basically, this is pretty much the same with the alkene. So mercury goes in, and they form the mercury ion, but they open up to the end because between these 2 carbons in the triple bond, this is a more stable position, right? Same, right? This is 2 carbons around this carbon. There's only 1 carbon, this carbon here. So they eventually form enol, okay? Because there's a double bond here, which is the ENE. This is hydroxylated by water, so the O, meaning the alcohol OL, so they form enol. But because of the do you guys remember this? Enol, keto, tautomerism. Okay, tautomerism. Okay, so meaning when they form the enol, okay, when they form the enol, they go back to the ketone position. So they form this one. Because of the alpha substitution, it will be covered in chapter 21, which we will cover in over 2. So that's why I didn't explain last time as well. But because of the eno keto tautomerism, when they form the hydroxy group on the more substituted carbon, but you still have a double bond because this is a triple bond to the double bond, right? So for alkene with no problem, because alkene double bond, now when you get the hydroxy group on the more substituted carbon, it's just a single bond, so it's no problem. But problem is hydroxy group with a double bond, which is what? Where you can have a pair bond, pi electron can be easily used to make it ketone, and they can be just gone too. And also this is better stability in the keto position. So we do eno to keto. So the equilibrium point is like this. So once they form the eno, they tend to form into the ketone position. Again, it's like this. That's why eventually you get this one. You get the eno part already what we did for the alkene, but for the triple bond, you can do even further because you still have a double bond that goes into the ketone position, which will be covered more detail in chapter 21 in order to. But okay, let me just. So here's the trick. So if you have some R group here in the terminal. So this is hydrogen. Okay, this is the terminal alkene. Alkyne. And then only thing you have to do is try to make it like a ketone here. So there's two carbons in the triple bond, and the one inside, which more substitute, will be carbonyl groups, and the other one will just become methyl group. So it will be ketone, because this is another R with the carbonyl groups in the between. It's ketone, right? So that's what let's do one more thing. Yeah, maybe you can do this one, okay? Real quick. We'll do this together. Okay, so look at the terminal alkyne. You have two carbons at the end with the triple bond. The one inside will be more substitute, put the carbonyl groups, and the other one becomes methyl group. That's the trick. It'll be much easier with that simple trick. Okay. Okay, so for this one, just saying, I'm gonna remove the triple bond. Okay, I'm gonna put, and between these two, I'm gonna put this one is more substitute. So I'm gonna put oxygen with the double bond, which is the carbonyl groups. So there you go. Yeah, makes sense, right? Just if you have a terminal alkyne, just remove the triple bond. The one inside is more substitute. Put the oxygen with the double bond, which is carbonyl group, and that becomes this methyl group. Okay. Okay. Right. That's it. So this is trick you can do. I'll just stop here today. Okay. So.